Okay, good morning. So we actually start a very important lesson today, and that is the topic of combinatorics. And then in particular, we want to spend time to understand the product rule or the product principle today. Um, so actually, this is, if I want to tell you what is the topic here, is I think it's a good phrase to say we count without actually counting. Yes. For example, we know that, for example, I think in Sweden, the car plates have 3 English letters and followed by 3 numbers. I don't know if 0 is allowed in the numbers, but usually they are not allowed, are they? Okay. So if we have 3 letters, for example, A, B, C, this is a typical car plate here in Sweden, for example. And then you want to know how many cars we can register using this trick, using this way of registering. Of course, this is not a hard problem, yes? One way is to start writing all of them down and then start counting them. Yes, this principle, this is not a hard problem. But we want to know that number without actually going through the process of counting one by one. So at the end, we want to count this number of plates, but without actually going through the counting process. So actually, that's a very good idea to define combinatorics. So we want to count without actual going to the process of counting, yes? By the way, so how many car plates do you think we can register if we want to follow this system? Because this is actually important, yes? Or how many personal numbers we can follow. So the people should, I don't know, the people who are in charge, they have to decide about if they want to set up a system. They should know when this system crashes, because if the number of cars is more than the number of plates that we can register, then we have to choose something else, yes, from the beginning. Okay, so these kinds of things, hopefully you understand this is important. So the nature of these problems, this is a misguiding idea, because the answers are so simple to write. When you see the solution, you are multiplying some numbers together. This gives you the wrong, sometimes, impression that they should be easy to understand. I mean, these are actually very easy to state, but sometimes extremely hard to answer. There are many open problems that people haven't solved yet in this topic. Okay? So, yeah, for example, this is one of the questions. The statement of the question is clear. It is not a very hard subject to understand, but might be answering this is a little bit harder than when you want to do it in practice. It's a little bit hard. Okay, so the first thing we want to talk about it today is the product rule. This is actually so simple that they call it the principle. When I state it, you will really understand what is going on. For example, we had it before. Do you remember? For example, if I give you A to be the set consisting of A and B, and if I give you, for example, B, the set consisting of C, D, and E, do you remember we talked about the Cartesian product of A and B? And then we want to know what is the cardinality of the Cartesian product of these two sets. So if you remember what we do, we take A with C, yes, and when we take A with D, and then we take A with E, and then finally, so we come back here and take B with C, B with D, yes, am I doing it right? Yes, and then B with E. So you can see that I listed all the elements, then I can start counting them. Yes, but this is actually the product rule or the product principle. You say that, okay, if I want to set up my set A cross B, I need to have this is a task that can be accomplished in two states. Yes, two stages. The first stage, because what I need to put in my set, I need to put an ordered pair there. To construct an ordered pair, my brain decides about two things, yes? Decides about what to choose for the first component and what to choose for the second component, yes? So then, for example, because I know the rule for the Cartesian product, I know according to the definition of the Cartesian product, stage one, what is a stage one for doing this act? So I say that the stage one is choosing the first component. The first component, yes? Stage two is choosing the second component, yes? So you might think that I am exaggerating the problem, but please listen to me that I have enough experience in these kind of things. You need to think in this way. Even if you're lazy, you don't write it down, but you have to think in this way, at least in your head. So I want to do what? I want to know how many possibilities are in front of me if I want to actually set up this Cartesian product. Okay? So you know that if I want to set up my Cartesian product, I have to put ordered pairs into the Cartesian product. But what is the rule for putting ordered pairs? I know from my studies that the first component should be chosen from the first set, and the second component should be chosen from the second set. So this means that even though I can do it very quickly in my brain, it's not hard subject, but to be honest, my brain probably goes through this process. If I ask you just give me a random, ordered pair in A cross B, what do you say? For example, you might immediately tell me AE, yes? But what your brain has done, your brain has decided for something for the first component and has decided for something for the second component. But this has been done because it was so trivial you even didn't think about it, yes? You just spit it out, A and E. But I actually solved a two-stage problem. The stage one was my brain chose something for the first component, and after that, my brain chose something for the second component. But the first component can be done in how many ways? How many choices I have for making the first stage done? Because I know the first component is supposed to come from A, and I see that there are two elements in A, so I would say that the number of ways that I can do the first stage, let me write it with n sub 1, the number of ways that I can do the first stage is 2. Now, after this first stage is accomplished in one of these ways, it means that either I choose A or I choose E, then my brain is supposed to decide about saying something about the second component. So in how many ways second component can be done? So how many choices are in front of me if I want to make the second component? Yes, it is 3. But this is something very important I will emphasize later. When you say 3, do you think this is independent from the choice you made for the first part, or it depends to how you have done the first part? This is extremely important. I will actually emphasize this later. So the first one, I have 2 options available. But when you said to me 3, you have to think about, this is the only thing you have to think. When you say 3, is this number affected by the way that you do the first stage or not? No, because in the first stage, if you choose A, how many options you have for stage 2? 3. And it doesn't matter if in stage 1 you have chosen something else, but still how many options you have? You have 3. Yes, if I have chosen B in the first stage, for the second stage, still I have 3 choices. So the number of ways that I can accomplish stage 2 is independent of how stage 1 is accomplished or done. Yes? If that is the case, then I can use the product rule and then multiply them. So I would say that the total number of elements, the total So I would say the cardinality of A cross B is actually n1 times n2, which is 2 times 3, and which is 6. Yes? Is that clear? This is the content of the product rule. In the first few examples, I will write a lot probably. You might say that, okay, these are boring. But believe me, if you don't train your brain to think in that way, then you will be in real trouble. Of course, some actions have some natural order associated with them. For example, if I ask you to give me an ordered pair, usually you will start from left to right. But if I say that, okay, can you give me another random ordered pair from here, some person might say C and B. Okay? Yeah, it's a little bit strange because they're not following the order, but it doesn't. Yeah, let us see how it works. Do you think I can interchange these stages? Okay, even though it is not very natural. So can I say stage 1 is choosing the second component? Yes? And stage 2 is choosing the first component. Yes?
Yes.
Let us see if it works or not. But these are things that becomes important in a while. So if I say that choosing the second component is my first stage, then how many options are available for me? 3. And then assume that stage 1 is done in one of these ways, and then you go to stage 2, which is supposed to be choosing the first component this time. How many options are in front of me this time? 2. Is this 2 independent of how I have done the first stage? The answer is yes. So then it becomes 3 times 2, which becomes exactly 6. Yes? Even though this is probably not natural for our human brains to choose this the other way around, but this is also working. Okay? So if we want to actually introduce this a little bit, so can you see that? Yes? Okay. So here we want to introduce the product rule. I don't know if this is working or not. Let us see why this is not working. Yes. No, this because I made it in Mac. I think this is not compatible with Windows. Let's see if it works. Yes, it works. I don't know for some reason. Okay, so this is the product principle. So what is the product principle? Is I want you to know the complete statement of this one. So suppose that the procedure of doing a certain task can be broken down into 2 stages. Yes? And then suppose that there are n1 distinct, so these are the words that I have emphasized. There are n1 distinct ways to do the first stage, and after the first stage is accomplished in one of these ways, the second stage, again, independent of the choice made in the first stage, can be accomplished in 2 distinct ways. So this, you have to really respect all these parts that I have written in italic, okay? In that case, what happens, then the task can be done in n1 times n2 distinct ways. And so that is the statement of actually the principle, product principle, or product rule. Okay, so if I want to give you an example, so let us read this example. Of course, this is more or less the same thing. In how many ways a team consisting of 1 mathematician and 1 physicist can be formed if there are 3 mathematician candidates and 4 physicist candidates? But it's an extremely simple problem. So assume that you really have a project going on, and then how many physicists or how many mathematicians are there? So mathematicians are what was that? 3, and physicist was 4. Of course, when you see that I have 3 mathematicians, so they are humans, so they are distinct entities, yes? So there are objects. By the way, when it comes to mathematics view them as objects, yes? So P2, P3, and P4, yes? Even if they are twin, they are distinct. So this distinctness is important because later we will see that what happens if some of these are not distinct, okay? So we have 3 mathematicians and 4 physicists. We want to set up a team for doing some project work, for example, or whatever. We want to see how many ways we can do that, okay? I want you to write these things so that your brain becomes ready for this topic. So what is your task? Let me write the task. What is the task here? You need to think, what is the task I'm supposed to do to set up the team, okay? Setting up the team. You just need to write something. The team. Yes? So this is the task you want to do. This task can be done in 2 stages, yes? Because you have to choose a mathematician among 3 people, and you have to choose a physicist among 4 people, yes? So what you can do, you can say that, okay, stage 1, you should have a definition in your mind for a stage 1, whatever you want to relevant to the problem. Choosing a mathematician, yes? Yes. And then stage 2, and choosing a physicist. Okay? So stage 1, answering to the number of stage 1 is always easy, okay? So a stage number 1, in how many ways a stage number 1 can be done? Yes? 3, because I have 3 options available, 3 mathematicians, I want to choose one of them. If there are no restrictions about their knowledge or something, if all of them are suitable, then I have 3 options. But then, you have to think in this way. Now assume that the first stage is accomplished in one of the ways. What does it mean? It means that either the first mathematician is chosen, or the second one, or the third one. The first stage is finished. Now you want to go and find how many ways I can do the second stage. So that is called N2. But in how many ways I can do this one? 4. But this you have to be careful when you want to write 4. I will give you examples. What do I mean by that? When I want to write 4, I always think, this number that I put here, is it independent of the way that the first stage is done? If the answer to this is yes, you write it, and then the product principle is applicable. Okay, I will give you an example that this is not the case. Okay, so then what happens? So that means that the question mark is n1 times n2, which is 3 times 4, which is 12. Yes? So I can set up this team in 12 different ways. Is that clear? Okay. By the way, can I change the stages here? I started with a mathematician, but you might say the stage 1, I decide to choose a physicist and then choose a mathematician. So it will work, yes? So the first stage becomes 4. There are 4 options available then. Then this 3 is independent of how I have done the first stage, so I can multiply 4 by 3, but the answer is still 12. Yes? Okay, so let us now go to the next example. This is also good. I want you to understand what we are counting exactly. So in the last example, we saw that there are 12 distinct ways to form the team. List all the possibilities. Okay, I want you to understand it better. So what do I mean by listing all possibilities? So what are those possibilities actually? What are they? For example, if you don't mind, let me just write a tree diagram. It might be easier. My first stage is to choose a mathematician. How many choices I have? I have 3 choices. So M1, M2, and M3. If I choose M1, how many choices I have for the second stage? 4. It doesn't matter, by the way. So it becomes P1, P2, P3, and P4. So this is also important to understand. But assume that no, I didn't choose M1, I chose M2. Then still how many options are available? exactly the same options are still in front of me. And the same thing for this one. So when I say list them, it means that, for example, you can say my team is M1P1. This means that I have chosen the first mathematician and the first physicist to be my team. Or I can say that M1 is chosen, but P2 is chosen. Yes? So you can immediately realize that I can continue this list. So I want you to know, what did we count? That 12 is the number of possible ways that we actually come up with without actually writing them and counting. One way of understanding this is clear. If I ask you how many branches you see at the end, you say that I have 3 branches here. For each one of these branches, I have 4 branches coming out. So in total, I have 3 times 4. Yes? And that is 12. So that's also, I want you to understand this. Okay, so let us now go to the next one. This is the remark I want to mention. Let me emphasize it again, because that is actually important. The phrase independent of the choice made in the first stage in the statement of the product principle is the key to correctly use this principle. Okay? This point is illuminated in the following example. So let us see why I emphasize so much on actually this. This is the example we want to talk about today, right now. So there are 5 roads, A, B, C, D, and E, that connect 2 towns X and Y. Okay? Consider the following cases. I will show you the cases. If the product principle is directly applicable, use it to find the answer to the problem, and if not, motivate your answer. Okay? Is it clear? So the first stage is this. In how many ways can one travel from X to Y and then return back if one is supposed to use a different road in return? Okay, so let us just keep it like this and try to solve the problem here. And then there is a second one. Okay, I want to emphasize what do I mean by being independent from what we have done before. Okay, so the problem is this. I have 2 towns, say X and Y. There are 5 roads connecting these 2. And then I have called them in the problem to be the road number called A, B, C, D, and E. Okay, so you read the problem. So, and then by the problem, can you tell me what is my task? So assume that you are planning your journey. According to the problem, the task is going from X to Y and coming back. And not being bored or something, you want to choose a different road in return than the one that you used to go. Okay? So this is the task, okay? Let me make it something. You have to have this task in your head. I am not forcing you to write it down, but you have to think about it. So what is the task? The task is to go from X to Y and back with different roads, distinct roads. I'm just making it short, okay? I really emphasize to think about in this way. Okay, now this is your task. So you want to go from X to Y and back, but you know that you're not supposed to choose the same road. So can this task be broken? This task can be broken into 2 stages, yes? One stage is choosing a road for going to Y, and then the second stage is choosing a road going back to X, yes? So stage 1, going from, no, let me write. Stage 1 is not going. Stage 1 is choosing a road from X to Y. And stage 2 is choosing a road from Y to X. But of course, by the condition given in the problem. Yes? Okay, so this is stage 2. Okay, stage 1, how many options are in front of you? So we call it N1. How many options do I have? Yeah, everyone, 5. But when you say 5, you need to think in this way. Assume that the first stage is accomplished. It means that you chose one of these roads for some reason and you are done. Okay? After you are done, you want to answer the second one. How many options are available for you when you come back? 4. Be careful, this is important. When you write 4, is this 4 independent of the choice you made in the first one or not? No, be careful. I mean, depending on which one you have chosen, do you think it will affect this number 4? This will not affect. Of course, this has an effect, yes? Because of the problem, I chose something, I am not allowed to choose the same one. So it will affect the number, but it affects the same way, yes? So it doesn't matter how I did the first stage. The second stage, without doubt, can be done in 4 ways, yes? For example, if I have chosen road A, in return, I am not allowed to choose road A. What I am allowed to choose B, C, D, or E, but how many ways are there? 4. Okay? Now assume that in the first stage I chose B. Of course it will affect how I am allowed to choose this, but it will not affect the number of my choices. Yes? So this is what I'm saying. The number that you put here should be independent of how this is done. Yes? Okay, so you see that for any one of them that I have chosen to go from X to Y, in return I have 4 options, independent of how the first stage is done. Okay, so is the product rule applicable, product principle applicable here? The answer is yes, because the second stage, okay, so the total number of ways that I can do that is what? So, the question mark is just N1 times N2, which is 5 times 4, it means 20. So I have 20 options available. Okay, so this becomes 20, yes? If I want to draw a diagram for you, might be you can understand it better, yes? So in going from X to Y, how many options are available for me? A, B, C, D, and then E, okay? But now assume that you have chosen A. In return, how many options are available for you? 4, but what are they? B, C, D, E. If I have chosen B, but still how many options are available? 4, but of course the options are not the same options as before, but this is not relevant. The number of branches coming out should be exactly the same again. So here, if I have chosen B, the choices that I have for return is A, C, D, and E. The choices for the second part is of course different from the choices that I have, but still I have 4 branches coming out. Yes, the second number is important. And of course, let me just do this one as well. So if I have C, how many options I have? Again 4, but what are they? This is A, B, D, and E. So you see that, of course, my first choice is affecting my second choice in how doing it, but not the number of the choices that I want to make for the second stage. So this means that the product principle is applicable. Is that clear? Okay, now let us go to the second part of the problem. So the second part tells you that if 2 roads, A and B, are one-way roads from X to Y, then in how many ways can this be done? Okay, so the problem is the same, but roads A and B are one-way roads from A to B. Okay, so this means what? I have this one, a one-way road, and that is also a one-way road. Let us try to understand the problem, because I think this is one of the simplest examples you will understand what do I mean by independent of how the first stage is done. Okay. I don't want to write it down, so the task is still the same task, yes. Stage 1 can also be considered the same thing. Stage 2 can also be considered the same thing. So if you want, you can write it once more. Okay, but let me write. Stage number 1, you want to decide how many ways I can accomplish stage 1 of this task. How many ways?
5.
5 ways. Yes. But be careful. Now stage 2. Stage 2, in 2, you want to answer something here. Can you definitely answer this number, or you need to know how the first stage is done? If you need to know, then it means that the principle is not applicable. If you don't need to know and you can write a fixed number there, then it means that the principle is applicable. Is that clear? Okay, now you answer me. Is it possible to say definitely what?
3.
3. So you say definitely 3. If definitely is 3, even without needing to know what is happening here, then it means that the product rule is applicable. The answer is 15. Okay? Okay, I forgot to record this anyway. Yeah. Okay, so what happens? So now I have 2 rows. So Gustav said you can definitely write 3 here, but how many of you agree? Yes, please?
You can also take, there could also be 2 ways you can take, if you...
Yes. So this is not definitely 3. It might be 3 or might be 2, depending on how I have done this one. Let us check. So this is not definite answer. This is 3 or 2. Why is that? For example, the first stage, I do not have any problems again, yes? How many ways I can do it? A, B, C, D, E. Okay. Now assume that I have chosen A for going from X to Y, and I want to come back. When I want to come back, of course, I am not allowed, according to the problem, I am not allowed to choose the same road. So how many options are available for me? 3. Because I cannot choose B, because B is one way. A is already chosen. Of course, that's also one way. So there are three choices in front of me, which are C, D, and E. Do you agree? Now let me choose B. How many options are available for me? 3 or 4? Again, 3. Yes, I have chosen B. I want to come back. I am not allowed to use this one because that's one-way road. I don't use this again. Again, I have 3 options. So it is C, D, E again. Yes? But now assume that I have chosen C in going. Okay, if I've chosen C, now I am in the situation that I want to come back. According to the problem, I don't want to choose C. But technically, I cannot choose A and B. So how many options are available? 2. And that is only D and E. Okay? And then let us just complete this tree diagram. And how many options are available if I choose D in going? 2 again. Yes, but they are C and E. And finally, if I have chosen these, what are they? C and D. And it is clear you cannot say 3 times 5. Because even though I have 5 branches coming out, but from some of branches, 3 more branches are coming out, and from 3 branches, 2 more branches are coming out. So if you just say 5 times 3 is wrong, if you say 5 times 2, that's also wrong. That's what I want you to understand, the difference when I want to write. You see, all the time this is affecting, it is also affecting in my choices, yes? So the choices that I have for the second stage are B, C, D, and E. But here it's A, C, D, E. But still I told you that the product rule is applicable because it is even. I mean, it is exactly the same thing for all the branches. Yes?
Will you say that stage 2 is independent now or dependent?
No, this is dependent. Because the number that I want to put here depends on my first choice. Yes? Either I have to put 3 here or 2. But when you say either this or that, it means the product rule directly is not applicable. And the product principle is actually not sufficient to solve that problem. Because you can solve this part of the problem by the product rule, and you can solve this part of the problem by the product rule, then you need another rule, which is the sum rule. These are very simple things, yes? This is a very simple problem. If I ask you finally how many ways I can choose my trip, how many ways? I have 6 options if I have these choices. And then how many options I have? 6. Again, 6 here, because this is 2 times 3, this is 3 times 2. So in total, I have 12, but I have to add them later. Yes?
Can I ask you, if you start the journey from Y, you don't see this problem with the 2. If you start your journey and choose, you have to...
No, but that is a different problem. There is no natural order here. I am in city X. I cannot start my trip from Y.
Okay.
Yes? So is that clear? Anyway, so this is why I want you to understand. I really recommend you for the first few problems, try to understand the task in your head at least, and then try to write down these stages, and then the first one is always easy, because there is no limitation, but for writing the second one, you just ask this question from yourself. Is the number that I put here is independent of how I have done the first stage? If the answer is yes, it means that the product principle is directly applicable. If not, we need more rules. Okay? Is that clear? Okay. Okay, so here I just wanted to test this idea, so I don't have more slides, but don't worry, we go to other problems here, okay? Okay, let us try to understand this product principle. So example 4, using the product principle as answer the following questions. How many 2-digit numbers are there? It is an extremely simple task. You even don't need the product rule to answer the question, but I want you to think in this new context. Okay, and then we want to see how many 2-digit numbers without repeated digits are there. Okay, so we want to solve this problem. Even though answering this, you already know the answer, by the way. What is the answer to the first part? How many 2-digit numbers are there? Yes? 80? Is it? Is it? Does it make sense? 89? Yes or no? It should be 90. Yes?
Get 9 options.
Yeah. So it is 90. Do you agree? If you don't believe, you have to count. This is not hard. By the way, it's a very good opportunity if you want to improve your programming skills. Yes, to be able to generate these lists and count them, okay? That's a good programming exercise. Okay, so let me just now try to solve this problem. Okay, I want to wait for you to tell me. For example, if you want to solve the problem in this new setup, you need to think about the task. What is the task here? Just make a story, okay, which is relevant to the problem. So what is the task? Writing down a 2-digit number, okay? You don't need to write a novel story, okay? But task is, what is the task here? Write down a 2-digit number. This is my task, okay? But this task, even though when I ask you just say 25, you just do it very quickly, but I don't know at the level of neuroscience what is happening in our brain, but probably when I say 25, in some way I decided about the left digit to say 2 and the right digit to be 5, yes? Because I could have other choices, but I said something 25. Might be there were some decision made in my brain, yes? Even if I'm not aware of. So this means, this way of thinking, this is my own experience. This will help you in these kinds of problems. So what can I say for stage 1? My brain decided about something, and that is choosing the left digit, yes? Something like that, choosing the left digit. And then I can say stage 2, choosing the right digit. Of course, this is called the units digit, and this is called the tens digit. But let us just consider this. Okay, is that unreasonable for you, this kind of a story, yes?
Does it matter which?
Then we come back to this because these are important questions. Okay, now tell me how many options I have for N1. How many? 9. Because I have a limitation, yes? If I want to write, you don't buy, when I say 02, you don't say that this is a 2-digit number, yes? That it cannot start from 0. But how many digits are there? I have from 0 up to 9, which is 10 digits, 0, 1, 2, 3, up to 9. But 0 cannot be chosen for the first digit. So how many options I have? 9. Do you agree or not? Okay, but the point is that here you have to be careful. You really don't need to be that careful there, it's very trivial. But when you want to say N2, how many options are in front of me now? 10. When you write 10, you have to be a little bit careful and ask yourself, is this number that I put here is independent of what I have chosen for the first stage or not? What does it mean? It means that assume that for the first stage you chose 2. Then how many options you have? For the second stage, 10. Now assume that no, it is not 2, it is 3. But how many options you are left for a stage 2? Again, 10. Do you agree that this 10 that I write here is independent of how I have done the first stage? So this means that the product rule is applicable. So the question mark is N1 times N2, which is 9 times 10, which is 90. Yes? So there are 90 2-digit numbers. Okay? But we can answer much more interesting questions than that later. Okay? I want you to understand this. Let us come back to the question that you asked. Even though this is the natural way of thinking, people write from left to right when they want to write numbers. But is it a necessity? If I ask you to write a 2-digit number, might be you write this. Yes, but that's also a 2-digit number. Might be you choose this one first and that one second. Okay, let me understand this one. So stage 1, choosing the right digit. Okay, be careful about that. And stage 2, choosing the left digit. Okay, now tell me, choosing the right digit, how many options are available for me? 10. Because I am talking about the right digit. So N1 in this set, in this new order is 10. But what is N2? N2 means choosing the left digit. 9. When you want to write 9, you have to be careful here now. Because this is the second stage. Is this 9 that I put here independent of how I have done this one? Again, yes. So again, principle is applicable, but the answer becomes 10 times 9, but you get the same answer. That's 90. Is that clear? Okay. Now, let us go and solve the second part. In how many 2-digit numbers, or how many 2-digit numbers without repeated digits are there? With distinct digits. You can answer it immediately, more or less. But let me just go back here. Now, write down a 2-digit number with distinct digits. Yes, digits. Yeah, something like this. I just want you to think about these things. Stage 1, do you think is also a good thing to write for stage 1? If I ask you to give me a 2-digit number without with distinct digits, of course you don't write 33 because I don't want that, but you can say I have 35, yes? Yeah. So here, can I say that stage 1, let us keep it like this, choosing the left digit. And stage 2, again, choosing the right digit. Okay, how many options are available for stage 1? I want to choose a left digit. How many ways I have? Yes? Again, 9, yes? That's enough. But now, so let me write these numbers here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the digits that can be used in constructing numbers. Now assume that the first stage is done in one of these ways. Yes? But of course not this way. But then we want to go to the second stage. How many ways are in front of me? What can I write for that? Can I write 9? Yes or no? Okay, but be careful. This one is the one that you have to be careful. Is this 9 that you told me and I wrote it down independent of what I have done for the first stage? You need to think about it, okay? For example, in the first stage, I assume that I wrote 1, okay? So, for the second stage, 1 is no longer allowed to be chosen because I want to choose. So let me just clean that. How many options you see? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now assume that no. In the first stage, say for example, 4 was chosen. But how many options are left for me again? 9. Yes? Do you agree? So I hope that you are convinced now that this 9 you told is independent of how I did it. Okay? But of course, in principle, you have to check all the cases. But this is very trivial. Okay, so then the question mark becomes n1 times n2, and this is 9 times 9, which is 81. Yes? Okay, is that answer reasonable, by the way? Because we had how many numbers before? In total, we have 90 of them. But some of them have repeated digits. What are they? 11, 22, 33, up to 99. How many of them are there? There are 9. In total, I had 90, and now 9 of them are not acceptable, so that's also a good solution. You can take it off. This is called the complement principle. Okay, so that we will come back to this later. But this is 81. Is that clear? Okay, now let us go. Oh, I forget to record this anyway. So let us go to the next problem. I want you to think about that. Okay, I think this is Hossein. Actually, we answered the question. By the way, this is good. Example 5, in part A of the last example, could you consider the first stage to be choosing the units digit and the second stage to be choosing the 10th digit? And I think it's a mistake. There should be an S here and another S here. I don't know for what reason. Okay, and still use the product principle to answer the question? That was the question that you actually asked. We answered yes, we checked that. But do you think, what about part B? Can I in part B do the same? Reversing the order, okay? So, I mean, now let us see. Stage 1 is choosing the right digit. Stage 2 is choosing the left digit. Let us understand this problem again, okay? So if you don't mind, let me write it again here. So I clean it, and I say right here, I clean it, and I say what? Left. Okay, and then I will clean these numbers, and I want to wait for you again. So do you know that? The problem is exactly the same. I want to write a 2-digit number with distinct digits, but my question is that let us reverse the order, even though it is not natural, but we don't, so natural from human perspective, not from mathematics perspective. Let us see what is the consequence. Can you tell me how many options are available for me if I want to do it in this way? How many options I have from these digits to choose my right-hand side number? 10. Do you agree? Because 0 can be chosen there. Okay, I write 10. Now my question. How many options are available for the second stage now? Yes?
I get 8.
8? Yes?
It would be 9 or 8.
9 or 8. So you spoiled the problem, yes? Yeah, exactly. So this is not working. Do you understand? I want you to understand when you can use the the product principle or not. Let us try to understand. If I say 10, that is clear. One of the possibilities in the first stage when I write 10 is to choose 0. Do you agree? Yes or no? This is one of the ways that I could have done the first stage. This is one of the ways. Now, 0 is no longer applicable because I am not supposed to repeat the digits. How many options are available in front of me? 9. Yes? This is one possibility. But it is also possible, when I say 10, it is possible that I have chosen the number 1. Yes or no? Okay, now I want to choose the left digit from the ones left. Yes? But how many options I have now? I am not allowed to choose 0 because that's a left digit. So automatically 1, 2, 3, 4, 5, 6, 7, 8 options are left. So you see, I cannot definitely say 9. I cannot definitely say 8. It depends how I have done the first stage. It is either 9 or 8. Yes? So this means that if I just multiply them, it does not work. And it is not working because we know the correct answer is 81. But that is a minor problem. I want you to understand this point. Is that clear? Yes or no?
Yes.
Okay, so whenever you want to write a number for the second one, you have to check it really, the number that you put is one single number definitely, or it depends to the situation in the first one. If it somehow depends, forget about using the principle of product directly. You have to combine it with other rules. Is that clear? So you see that sometimes orders matter, yes? Sometimes if you reverse the order, it does not work, it does not change anything, but sometimes it changes. So sometimes it is important to care about the order as well. Is that clear? Okay. So now let us go to the next, this is a little bit more interesting problem. Example 6. All the questions here are more or less trivial for you because it's a two-digit number, but I hope that you agree with me. If I ask you the same questions regarding a three-digit number, it is not that immediate to answer. Yes? Because, for example, let me ask you this question. I want to write down a three-digit number with distinct digits. Just I want you to feel that this is not as simple as answering the two-digit case. Yes, because for example, I have to exclude 112 because this is repeated. I also have to exclude 111 because all of them are repeated. So there are many different cases coming in. So if you want to solve them case by case, that is not very efficient. So that's the reason that these things are a little bit trivial is because we are solving simple problems because I want you to understand the setup very good, okay? Okay, let us go now to the problem here. Let us do again everything. Use the product principle, answer the following questions. Yes? How many two-digit odd numbers are there? How many two-digit odd numbers are there? We want to answer that question. Okay? So, let me just modify this a little bit. Write down a two-digit odd number. Yes? I don't insist to write these things, but this you should write it in your brain at least, yes? Write down a two-digit odd number. Do you still agree that I can write the same thing for a stage 1? Yes? Can I? Because I want to write a two-digit number, but I want to be odd, yes? So I would say choosing the right digit. So let me write the natural way to do it, yes? The left digit, and then the right digit. Okay, so let me clean this and see how it works. And let me also write all the digits in front of you, so that... Okay, so this is the package of our elements we can use. Okay, tell me, in how many ways I can do the first stage? I want to choose a digit, yes. How many ways I can do? 9. Because the only exception that I cannot choose is 0. So how many options are left for me? 9. So I write 9. But now tell me, be careful. We want to write an odd number. So this gives me some restrictions for this second one, at the right-hand side digits. How many options are available there? Which are they? Either I have the choice for 1, 3, 5, 7, and 9. They are 5. So try to write 5, but be very careful in writing this second number. Is this 5 that you told me is independent of my first choice? Yes or no? For example, test this idea several times so that you get used to it. For example, assume that in the first one, you told me I have 9 options, so assume that I have chosen 1. Okay? And then, how many options I have here? No, be careful. I am not allowed to take it out, yes? Because I am allowed to reuse it again. Yes, that's the whole point. So when I say 5, when I say the first one has 9 options, because 0 cannot be chosen, but because I want to just write a 2-digit odd number, there is nothing in the problem to prevent me to repeat the same digit. So I do not eliminate it. Yes? So, and how many options are available? 1, 3, 5, 7, 9. 5 options. Now assume that I have chosen 3. Does it affect the number 5? No. But this means that this 5 is independent. Yes? So this means that the answer to the question is 9 times 5, which is 45, and it is reasonable. Because how many 2-digit numbers were there, do you remember? We just calculate 90, and half of them are even, half of them are odd. So that's 45. Okay. Now, what is the second part of the question? This is a good question. And how many of them does not have any repeated digits? I want to write 2-digit odd numbers, but this time with distinct digits. Okay? Okay. So here, now with distinct digits. Okay, now this is the same thing. I hope that you still agree with this one. Let me see if you agree or disagree. Let me keep it for the time being. Okay, what do you think I can do? Let us choose the left digit now. The problem is the same, but I'm not allowed to repeat a digit. Okay, how many options I have here? 9. Yes, I write 9. Now I want to choose the right digit in a way that the number is odd. Okay, how many options I have here? Yes? 4 or 5. It is not decisive, yes? It is not clear. Why? Because when you say I have 9 options, is it possible that you have chosen 1 in the first one? But here I am not allowed to use the same digit twice, so I just cross it over. I'm not allowed to choose it again according to the problem. And I still want to have an odd number. So how many options are available for making my number odd? I have 1, 2, 3, and 4. Is that clear? So if it happens that I have chosen 1 in my first stage, according to the problem, I am not allowed to use 1 anymore, but still I want to make it odd. So the number that I choose for the right-hand side should be either 3, 5, 7, or 9, which is how many options? 4. Yes? Do you agree? But there is no force behind me to choose 1 for the first one. It might happen that I have chosen 2. It is possible, yes, one of these 9 options. And then I still want to make my number odd. So how many options now is available? 1, 2, 3, 4, 5. So this becomes or 5. So is the product rule applicable? No. Okay? Either we have to give up, or we have to find another way. This is what I want to teach you. Sometimes changing the order of stages will solve the problem. Okay? Even though it is not the natural order for the human brain to do that. So think about this one. Sometimes the product rule is not applicable in some order, but suddenly if you change the order of the stages, even if it is strange from human point of view, suddenly it works. Okay? Okay, so let us try to see if it is going to work here or not. So, the problem is still the same, but stage 1, instead of making it left, I'm making it right. And instead of making it the second one, I make it left. and I ask you to think about the problem here again to see if it is working. If it is not working again, it means that the product principle in its own is not sufficient to solve that problem. We need more tools, okay? Okay, so let me just try to understand the problem again. Now, choosing the right digit. So the right digit, what I am allowed to put here, be careful, I want to make my number odd. Yes, everyone, how many options? 5. Either 1, 3, 5, 7, or 9. 5 options, so I would write 5. But because I am not allowed to repeat, one of these 5 numbers is crossed over. Okay, so let us, for example, say that 1, I chose 1. Yes? Now I want to fill up the left digit. Okay, I am not allowed to use 1 because I am not allowed to repeat, but there is also another exception coming in. I'm not allowed to choose 0. Yes? So I cross them over, and how many options are left for me? 8. Okay. When I want to write 8, I have to be careful. Okay? Assume that I haven't chosen 1. I had chosen 3. Yes, because I want to choose an odd number. Okay, how many options are available? I am not allowed to I am not allowed to use this one anymore. I also know that I am not allowed to use 0. How many options are left? 8. So it's still 8. So do you agree with me? Really, it doesn't matter. Yes? If I have chosen 5, if I have chosen 7, if I have chosen 9, this 8 is still 8. So this is working suddenly. Yes? So this means that the question mark is 5 times 8, which is 40. So there are 40 odd numbers with distinct digits, 2-digit numbers. Yes? We'll come back to see if this is reasonable in a moment. But do you agree with me now what is happening? In the natural order, it didn't work, and I want you to understand that it didn't work. And then I'm just giving you as my experience, sometimes the natural order does not work, but if you reverse the order for some strange reason that you still understand, it works. But if none of them works, it means that this is not enough, we need more tools. Okay? But by the way, let us go back. Do you think this number is reasonable? Could you guess this? There should be 40 odd numbers, 2-digit odd numbers without repeated digits. How many odd numbers are there? We learned 45, yes? Okay, so how many of them are not acceptable? 11 is not acceptable because 11 is an odd number, but this is repeating itself. The other one which is not acceptable, 33 is not acceptable, 55 is not acceptable, 77 is not acceptable, 99 is not acceptable. These are the only ones that are not acceptable. How many of them are there? 5. In total we have 45. Subtracting them, it becomes 40. So it is reasonably correct. Yes? So this is the experience I want you to learn. If you learn this one, I mean, you see that this is why I'm saying that the students sometimes are lazy to think in that way, because the answer to the problem is a primary school task. It's 5 times 8. So you might say that, okay, I have to write so many things because the answer is just 5/8. I don't insist you to write, but I insist you to do it in your brain in that way. Otherwise, you will be soon in real trouble, okay? Any questions? Okay, so as a rule of thumb, I want you to tell you this. If I want to start staging my task, I will start with the one with more restrictions. Okay, this is a rule of thumb. Sometimes it's not a mathematical argument. So for example, for making a 2-digit number which is odd, I have 2 digits, the left one, the right one. The limitation for the left one is only one case, and that is 0. I cannot put 0 here. But the limitation for here is not only 0, but 2, but 4, but 6, but 8, because I want to make it odd. So the limitation of the left one is one digit, 0 cannot be chosen. But for this one, 0, 2, 4, 6, 8 cannot be chosen. If I want to order the stages, I give the priority to the one with more limitations. It's just a rule of thumb. I'm not saying it works 100%. Okay? But if I wanted to solve this, because I had this experience before, I would have started from this order, even though it becomes strange. Because I would say to myself, okay, I have more restrictions for this than that one. So let me write choosing the right digit as my priority. Yes? This is a rule of thumb I told you that might be, does not, sometimes doesn't work. Okay, any questions? Okay, so if you don't mind, let me just wait for you, and then I want you to solve these two problems, and then we are... Actually, this is also a good problem, these three problems. Yes. Of course, the answer to these problems are extremely simple, but I want you to take this opportunity to be more explicit when you want to answer it. At least write something for the task, stage 1, stage 2, and things like that, okay? I want to wait for you. Yeah, this is an extremely simple problem, yes. Might be the only interesting one is this one. This is also a good problem. Okay, I will not continue the lesson to the generalized product principle, but we can continue next lesson. Actually, problem 7 and 8 are extremely simple. The only interesting one is number 9, probably. Okay, so, by the way, could you answer it based your intuition without this systematic way of thinking here? I mean, it is not that easy again. Yes, even though, you see, I'm asking you, assume that these are the only digits, and I'm asking you how many 2-digit numbers without repeated digits can be written. Of course, the list is so short that you can start writing them down and count them. It's not probably that big, but I mean, it is not that trivial as all 2-digit numbers. Do you agree? Because about all 2-digit numbers, we have something in our head, yes? I don't know, can you guess before doing it in a systematic way? I mean, if I ask you what is the number of 2-digit numbers, you immediately answered yes. Yeah, because you knew it was 90. But if I ask you the same question, that you are not allowed to use 5 or 6 or 7, 8 and 9 anywhere, the answer becomes even a little bit harder, yes? So you really need a systematic way to answer the problem, yes? So this is good. So what is that number? So let me just talk about it orally. So what is my task again here? My task is to write a 2-digit number with distinct digits. This is my task. But this task can be viewed as 2 stages. Yes? Stage 1, for example, let me write it like this to make it very simple for you. Let me write stage 1. Do you agree? Let us take this as stage 1, and let us take this as stage 2. Okay? Is it a good idea to start with the stage 1 here? Because I told you, for this one, I do not have any restrictions. But for this one, I have one restriction. So it is better to start with the one with more restrictions. So this is even, here it is natural, and actually according to the rule of thumb. So can you tell me how many options are available here? 4. So it is easy to write. If you want to be lazy, you can just write it like this. So stage 1 can be accomplished in 4 ways. But stage 2, how many ways are left for me? The condition of the problem is that I am not allowed to use the same number. So what can I write here? 4. So when you want to write 4, you have to be careful about if this is 4 or not. When I say 4 here, I know that I haven't chosen 0 here, I have chosen one of them there. Okay? And because I am not allowed to repeat, let me assume that I have chosen one and I'm not allowed to repeat it anymore. But when it comes to stage 2, how many options are available?
4.
So what you said is correct, but you have to double check. If I had done this one, do you think it will affect the number of choices here? It will affect my choices, but not the number of choices. That is important. This is still 4. And then this is applicable, so the answer is 16. Is that clear? So there are 16 two-digit numbers with distinct digits we can write, which was not that easy to guess. Of course, the list is so short that you can sit down and write all of them and then count them. Yes? And by the way, that is good. If you know Python or any other languages, try to generate this list and then count them. This is a very good exercise for the people who are trying to learn programming. Okay, so that's it. The other question is also simple. We have a word, almost, okay? And then it is mentioned that we want to do what? How many ways one can choose a vowel and a consonant from the letters of the word almost. That's also very simple. So what is the task here? The task is exactly the problem. I want to choose 2 letters, 1 vowel, 1 consonant, but I can break it into 2 stages, yes? For example, stage 1, the vowel one, yes? Stage 2, the consonant one. Okay, just make it simple, okay? And I do not have any natural order here, and I do not have any limitations that it affect the problem, so apparently it doesn't matter which stage I choose which one. So, stage 1, I want to choose a vowel from this word. How many of them are there? A or O, so I have 2 options here. I choose one of them, and then how many? By the way, you shouldn't say that, can I repeat it or not? These are standard things in combinatorics. When I give you the word almost, it means that you need to use only these letters. Yes, if there is 2 letters O in the word, then you can choose it 2 times, yes? But if there is only 1, you can choose it once. So, this is done, and then I want to choose this one. What is that? L, M, S, or T. Yes, so it's 4. Is this 4 independent of my choice here? The answer is yes, so this is 8 ways I can do that. Okay, but the interesting problem here is actually this checkerboard 5 by 6. Usually 5 is the number of rows, like matrices, and 6 is the number of columns. So we have a checkerboard or chessboard, dimensions 5 and 6. We want to see how many squares are there. 3 by 3. Okay, it's a good problem. So let me just draw something here for you on the board, and then we are done. So I have 5 by 6. So let me just draw something here. It's rectangular, 1, 2, 3, and 4. So make it 5, yes. And then, of course, all of them should be the same size, but don't worry about that. 1, 2, 3, 4, and 5. And then here, I have to clean the last part. Yeah, 1, 2, 3, 4, 5, 6, yes. I cleaned this one. It's not a very, let me make it a little bit organized. Okay, so this is my chessboard. I want to count the number of all 3 by 3 squares that I can draw within. By the way, this is a non-trivial problem. Yes? I can make this much bigger and ask you the same question. If you know how to do it, if you know how to do it systematically, it doesn't matter even if I increase the size. But if you don't know how to do it systematically, it becomes hard. In this case, might be you are patient, sit down and do all of them and then count them, yes? But if I increased, for example, say 1,000 by 10,000, then this method that I'm going to teach you will work, but the other method is probably cumbersome, yes? So, what can I do here? The task apparently is a little bit different from the previous tasks, yes? My task is clear. I want to draw, for example, drawing a 3 by 3 square within this checkerboard. This is my task. But there is no natural breaking stages. Yes? You might say that, okay, I don't know. This is why the problem a little bit is more interesting. My task is to draw a 3 by 3 square inside this. This is one of them. I can start from, for example, here. I can start from here. This is another one. So how many of them you see here till now? 2 of them. We want to consider all possibilities in a way that if I increase the dimension of this, you can still do the same thing. Okay? So the only difference between this problem and the previous problems is that the stages are not natural, at least. What I can call stage 1, what I can call stage 2. So this is the creative part of the problem, and believe me, you have to be super smart sometimes to be able to solve these problems. Okay, so don't get to this idea that, okay, I am stupid or something, I cannot solve this simple problem. No, these problems by nature are extremely hard to solve. Okay, I'm just giving you this warning. Don't blame yourself. Okay, so how can we solve the problem now? Yes?
What I'm thinking is we can find the number of squares where, like, the center of our 3 by 3 square could be. So, for example, on this one, it will be in all squares except the one.
Okay, but so I want you to, first of all, might be you have other ideas, but my point is that how can we relate this to the today's lesson, meaning the product principle? So in product principle, we need a task for the time being, which is composed of 2 stages. So this is why, how can I understand this problem in 2 stages, yes?
I thought you can place the square in 3 different places on the vertical place, and then on the horizontal place you can place it 4 different times and then multiply where you are.
It seems correct. So Hadia is actually talking about the stages. So if you don't mind, let me concentrate, for example, on the blue one. If you want to draw the blue one way is, of course, draw the blue one here. But if you want to systematically think about that, do you agree if I give you this point and that point, and if I give you this point and that point, you can draw the square. Yes? What do you do? From these 2 points, you draw 2 parallel lines, and from these, you draw 2 parallel lines. They will intersect somewhere and make you a square. So if I want to address this blue square, one way is to draw it in front of your eyes. Somewhere is just to give you the code. These 2 and these 2, then you can construct the square yourself. This way of thinking is extremely important in combinatorics in an indirect way. Yes? So now you see that I have 2 tasks. I have 2 stages. One stage is to choose 2 points with distance 3 from each other on the vertical line, and 2 points on the horizontal axis with distance 3. So I can break it into 2 stages. It was not direct, that is the hard part of these kinds of problems. So I would say that, okay, stage number 1 is to choose these 2 points with distance 3. How many ways I can do that? Let me make my fingers like this. So I have 1 option here. This is 2, and this is 3. I do not have any other options, yes? I can either choose this point and that point, or this point and that point, or this point and that point, yes? So how many options are available here? 3. Now assume that this is done, and then I want to see how many options are available here. How many? So let me just make my fingers 3 units. Yes, this is 1 option. I can choose these 2 points, 2, 3, and 4. Yes, so the second stage is 4. Is this 4 independent of my choice on the vertical axis? Yes. So this is 12. Yes, so it is possible. And if you increase the size, it is easy, it is not hard. Because how did I come with 3? 1, 2, 3, 4, 5, 6. Okay, I subtract 6 from 3, yes, because I want to have the length 3 units, yes. So it is immediately extendable to the any kind of dimensions. So you see the answer is so short, but the idea that takes you to answer the question in this way might be hard. This is the nature of these kinds of problems, yes. But that is very, very fun. We will enjoy this a lot, I think. Okay, any questions? Yeah, we stop here. Thank you.